Okay, so welcome to today's lesson. Today we are talking about how ions get formed and some of the different things, the patterns that go along with ions. The reason why we talk about ions a lot is because it turns out they're actually really important to us in chemistry. I shouldn't say that, a large amount of the chemistry that we do, especially in Chem 1, is related to exchanges of ions and how they react with one another. So it's kind of important for us to kind of understand a little bit about this process. So basic review. What's an ion? An ion is simply an atom with a charge. I'll remind you that you are not allowed to change the number of protons in an atom. So if it has a charge, that means there must be something different going on with the number of electrons that they've got. And with this particular thing, we'll talk a little bit more about how this process works. How do I know if they gain electrons or lose electrons? And so we'll kind of get into this more detailed stuff as we go. But most of our chemistry that we deal with is either about atoms gaining or losing or sharing electrons of some sort, or potentially coming up with a new partner, rearranging some different bonds. So this is really the underlying basis, this formation of ions, for most of what we do here in Chem 1. Okay, so basic definition stuff here. As a reminder that cations are ions that have a positive charge to them. So how do we understand some big ideas about what cations are? So cations, first of all, are formed from metals. Metals always lose electrons to become ions, and there's some important patterns here to start to understand. As we get through this, we'll kind of revisit this again, but alkali metals, our first family of elements that's on there, like the diagram on the top left, alkali metals always lose one electron to become an ion, and you can kind of see in that sodium atom, that third shell for that particular atom only has one electron in it. So it wants to get rid of that one, and when it loses one electron, it becomes a +1 charge. Things in the second column, the alkaline earth metals, become 2+ ions. Again, they get rid of two electrons and then they become a +2 charge. So cations are formed from metals and they always have a positive charge to them, +1, +2. You'll see a couple +3s and very rarely will you see a +4. On the other side of this is anions, and anions are the opposite end of this. If a cation is a positive charge, an anion is a negative ion. These are actually formed by nonmetals. They have a different style of electron trade that they like to do. Anions are formed when something gains electrons. So nonmetals are sort of missing an electron, and so they want to gain one or two or three to fill up a shell. It's a little bit different. The halogens, like fluorine and its family, all have one empty space, so they'll gain one electron to become a -1 anion. Things like oxygen and its family, they've got two empty spaces, so they want to gain 2 electrons to fill it up, and they become a -2 charge. We'll get more into this pattern here later on in a little bit. So this is just sort of a general overview of some of these big families, that you've got metals form cations and nonmetals form anions. And again, nitrogen's one of those other ones that'll do a 3- to it. So why is this? So we're going to kind of go into that backstory a little bit, and we'll come back around to the pattern here in a second. It turns out, you've probably seen pictures like this before, that atoms have a nucleus in the center, and then they've got electrons in the cloud on the outside, and those electrons are arranged in little regions that we call energy levels, or energy shells is another term for that. And a lot of times in a diagram, you'll see it look like this kind of a bullseye diagram. This is also called a Bohr diagram. There's some other names for it. The key idea to take away from this is that atoms, when they're stable, have full energy levels. And that number that they need to be full is a little bit different depending on the size of the atom, but for all atoms, in the small ones anyway, that first energy level is full when it has 2 electrons in it, and that means it's stable when it's full. The second energy level is full when it has 8 electrons in it, and the third energy level is stable when it has 8 in it. It's not full, but you don't really want to know the whole story of how many electrons it can hold at this point. So again, the typical rule here is for stability, to get a full or stable energy level, they will either gain or lose electrons. So they'll gain some to fill it up, or they'll lose some to kind of empty it out and drop down to a previous one. So energy levels and stability is the key idea. It turns out that some atoms are not very stable, but some ions are, and that's the important part. So let's take a look at this in terms of kind of a little bit more in depth. We'll use sodium as an example here. So this is about stability and having that 2-8-8 pattern or some variation of it. So what is going to happen to sodium? This sodium right here, if you take a look at this diagram, it's got 2 electrons in its first energy level. It's full and stable. Second shell there, you count them all up, has 8 electrons in it. It's full and stable. And this third shell has 1 and only 1 electron out there. That's definitely not stable. That's the opposite of stable. We would call that reactive. So what's it going to do? It's going to try to get rid of that one electron, because if it gets rid of that one, it then drops down to a stable configuration. So here's what that looks like when it does that. So here I've kind of shown a stupid little X through that last electron. Let's say it gets rid of it, throws it away, gives it to something else. And now it's got a slightly different arrangement. This is sodium ion now, because it only has 10 electrons, still has the 11 protons. In that first energy level, it's still full with 2. Second energy level has 8 in it. It's full and stable. And the third energy level is now empty. And believe it or not, that would be considered to be stable. It sounds kind of weird to say empty. That's okay to do that? Yeah. For atoms to empty out an energy level and kind of drop down to a previous full one, that's actually a huge advantage in terms of reactivity for these guys. So that's kind of how sodium takes care of its business. Let's look at another example here. With this one, here's sulfur. Let's take a look at what sodium likes to do, or sorry, not sodium, sulfur likes to do. Again, same idea. That 288 pattern is kind of the important rule for stability. Sulfur starts out with 16 electrons. So you can kind of take a look at the diagram here. In that first shell, there's 2. The second shell, there's also 8. It's full and stable. The third shell over here has 6 electrons to it. That gives the total of 16. But that third shell isn't quite happy. Remember, 8 is the stable number for the third shell, and it only has 6. So what is its option in order to achieve stability? It's going to, instead of dump out all 6 of those, it's going to just gain 2 more. It's a little bit easier. And it kind of comes down to that question, do I get rid of some or do I gain some? What's going to be the easier pattern here? So in this case, gaining 2 to fill it up to 8 is easier than getting rid of 6. So what does it look like now when it becomes its ion form? Here it is, sulfur with a 2- charge, sulfur ion. And it's got those 2 extra electrons in that last shell. So it now has a total of 18 electrons. It started with 16, gained 2 more. First energy level hasn't changed. Second energy level hasn't changed. But now the third energy level is full, and this is considered to be stable. So this is the sulfur ion, also known as sulfide, and it's got an S with a 2- charge after it. Okay. What do we do with this? All right. Third choice, number 3. Again, keep this idea of stability in mind. This is the element argon. Argon has 18 protons. It's over on the right side of the periodic table if you're looking for it. And take a close look at its electron shell. In its first shell, it's got 2. In its second shell, it's a little different diagram, but it's got a total of 8. So that's stable. And in the third shell, it has a total of 8. So what's this atom going to do? Nothing. It's already stable. It's got that 288 pattern already filled up. 2 in the first, 8 in the second, 8 in the third. Doesn't need to do anything. And this actually tells us something about noble gases. That's what argon is. It's in that far right table, far right part of the table. They're already stable. They don't need to gain or lose anything in order for them to be happy in a chemical sense. So they actually don't form ions at all. And that's why we really don't talk about them a whole lot, because they're really chemically unreactive. That's why they're noble gases, because they're too noble. They don't participate with chemistry. It's kind of below them. Okay. Kind of the next bit. I know this is probably a little bit fast, but in terms of the next piece, so where do those electrons go? So if sodium throws 1 away and sulfur gains 2, where do they come from? Well, the truth is that these are not atoms in isolation. Chemistry always occurs when you're talking about atoms that are coming into contact with other atoms. It could be as simple as throwing a chunk of sodium into water or leaving some chlorine out in oxygen or some other kind of a metal for it to react with. And the true thing here is that with these, they tend to find one another. So they form these beautiful partnerships where one wants to gain electrons and one wants to lose electrons. Perfect in terms of what they want to do. So here's a picture here that kind of represents what happens in salt, sodium chloride. Sodium atoms start off with 1 extra electron that they want to get rid of. Chlorine atoms have 1 less than they need. They've got 7 in their outer energy level, and they really want 8. And they need to gain 1 to become stable. So what do? They transfer 1 electron to the other. Sodium gives it away. Chlorine takes it. Sodium becomes sodium ion, and chlorine becomes chloride ion, and then that becomes a happy partnership. And in the end, we get this compound called salt, because these 2 ions are now attracted to one another because of their negative charges. Sodium's positive, chlorine is negative, and opposites attract. So they stick together basically just like magnets. And that's a lot of things that we call salts are actually held together by these ionic bonds. Okay, so, oh my God, do I have to draw these pictures every single time? The good answer is no, you don't. We're going to talk about some of the shortcuts here, but luckily there is a shortcut, so you can just kind of memorize a simple pattern for it. So let's take a look at the very first family on the periodic table. These are the alkali metals, and that's lithium, sodium, and potassium. These things are found vertically. So lithium's number 3, sodium's number 11, potassium is number 19. They're right directly in a single chemical family on the periodic table. And if you take a close look at them, they actually have something very similar in terms of their atomic structure. They all have a full first energy level, and then they may have a second or a third energy level in there, but their last energy level, the outside one, only has 1 electron in it. So if you take a look at lithium, its first shell is full with 2, but its second shell only has that 1 electron in it because it's got a total of 3 to work with. Sodium kind of follows a similar pattern. First shell is full with 2, second shell is full, it has 8 this time. But then again, the outside one only has 1 electron in it. And if we go all the way to potassium, it's a lot of dots to draw. First shell is full with 2, second shell is full with 8, and the third shell is stable with 8. And then that fourth shell, all the way up to number 4, it still just has that 1 electron on the outside. So there's this consistent pattern as we go down a chemical family. In this case, that alkali metals each only have 1 electron in that outside energy level. So all of them are going to follow the same pattern. They're all going to give away that 1 extra electron to become +1 cations, all of them. So once you get the idea that there's a pattern vertically, once you kind of figure out the charge of one thing in that family, you know the charges of kind of everything in that family. So without really drawing out every single diagram, we can kind of realize that there's these systematic patterns of atomic shape. It's easier to draw out small atoms than big atoms, but the good news is that this pattern holds from left to right across the periodic table. So again, without drawing every single one of them out, I'll let you do that if we want to, or we can do it in class. Here's your basic patterns. These numbers across the top are the ones that you want to really look at. And it's a pretty simple pattern. If you can count to 4 and back down to 0, you can handle this. But the rule here is that the whole first family, the alkali metals, always becomes +1 cations. The alkaline earth metals always become +2 cations because they have 2 electrons to give away. Boron, aluminum, gallium, these guys over here in this third family become +3. Carbon, silicon, germanium, these guys in the fourth family here, they can become +4 or -4. They actually have 4 electrons in a shell that can hold 8. So they could gain 4 or they could lose 4, just depending on what they want to do. Nitrogen's family all becomes -3 ions. They've got 5, and they want to fill that up, so they get up to 8. Oxygen's family all becomes -2s. The halogens all become -1s. And then, as I mentioned earlier, all the noble gases don't become ions at all. So again, you can either figure this out from memorizing the little pattern, +1, 2, +2, +3, ± 4, -3, -2, -1, or you can figure out the long way if you want to draw them out. It's fine either way in terms of what you are, but a lot of times it's nice to be able to look at the periodic table and cheat, right? 1, 2, 3, 4, 3, 2, 1. The middle part down here, notice how this is kind of fuzzed out. This part gets complicated. We'll talk more about this. Basically, the short answer is they have more than 1 charge. There's no easy pattern, and we'll talk about that in the next unit, so don't worry about it right now. Okay, so in terms of what you should be able to do as a result of this particular little lesson. Number 1, kind of review. You should know what an ion is and be able to tell the difference between a cation and an anion, especially in terms of gaining or losing electrons. You should be able to figure out what the charge is of an ion based on gaining and losing electrons too. So if I say it's a -1 charge, that means it's gained 1 electron, or -2 because it's gained 2. Or if it loses 3 electrons, that becomes a +3. You should be able to kind of have that idea that stability is the key point. That in terms of ions becoming ions, they're doing it to become more stable. So if you get rid of an electron, it may make an ion that's more stable than the original atom that it came from. I know that's kind of an unusual idea that a chemical reaction can make it stable, but that's kind of the process on there. You should be able to kind of get that idea of linking those two pieces together. That it's about trying to get that 288 pattern or something like that that allows it to either gain or lose a couple of to try to get towards a stable configuration. You should be able to draw some pretty simple energy level diagrams. I know we went through that pretty fast, so you might have to look at it really closely to kind of see what that pattern is. But given the number of electrons, you should be able to draw those simple bullseye diagrams or energy level diagrams, knowing that 2 electrons go in the first, 8 electrons go in the second, and 8 usually goes in the third. We won't do anything real big. So basically atomic numbers less than 20, you should be able to kind of follow this pattern. And then finally, you should be able to use the periodic table patterns to predict the charges of ions, the simple charges. So if I just give you something like sodium, you should go, oh, it's in the first column, it's a +1. Oxygen, count it over 1, 2, 3, 4, 3, 2. Oh, it's a -2. And that's what I'm referring to with this particular periodic table pattern. So there you have it, being able to look at some information about how ions form, some introduction to some patterns across the periodic table, and some information about atomic structure and how that relates to ion forms. So we'll talk to you in class, and we'll see some more examples of how this works. Good luck with this.